So hello, everyone. My name is Jaehyun So from Aju University. Maybe some of you guys don't know where is Aju University and what kind of university that is, but this Aju University is in Suwon. It's a 1 hour distance from Seoul. You're probably the students from Korean, they very well know that city, but it's a 1 hour distance from Seoul. And actually, professors Inhee Kim and Kite Chang, we are we are very close, and we are working together in many projects. So that's the reason why. So probably I'm introducing myself because I talked to Inhee and we are talking about that. So I'm lecturing in Aju University, and we are well known. So I brought my introduction page so I can make this lecture start with my introduction. So just having some free time there. So that's my kind of gift to the professor. So today, I brought this title toward autonomous vehicles as mobility solutions, and the subtopic is a spectrum of research in transport engineering. Actually, I changed my subject because some of you guys probably recognize today's title is about some kind of the use case of data analytics in transport engineering. Because first time I've thought about this seminar was to prepare some kind of some research, one specific research case using data analytics, because that's what I'm focused in these days. But that's just one specific topic. But I would define myself, I'm not very deep in those kind of data analytics. I'm just using that as an application, and I'm not a data scientist. So instead of just presenting just one specific topic, then I decided let's share with you what I'm interested in and what I've done so far. So I decided not just one specific topic, and just let's share kind of spectrum of research in transportation engineering in the objective toward autonomous vehicle as mobility solution, not just a vehicle technology. And my goal is to make it like working in a real field and working as a mobility solutions. So there are so many things to touch up from transport engineering. So probably what I'm presenting is not all about the transport engineering, but probably it's gonna be part. But anyway, I have done some of the part from transportation engineering for the autonomous vehicle research. So that's what I want to share with you. So before we get further, I brought some introduction page introducing myself and my lab and so those kind of things, and then prepared some 5 seminar parts. But it's 1 hour lecture, right? 1 hour lecture including the question and answers, right? So not gonna it could be very long. So I'm gonna just focus on some of the things, not just all. And then some of the things I'm gonna just introduce what that is. So if you have a question on specific topic, and if you have something to collaborate with me, then just let me know that we can have another seminar and more kind of deeper and focusing on some specific topics. So let's go on next. Just want to talk about myself, and then actually I graduated Aju University. That's what I'm working for now. Yeah, maybe it's communication delays. So graduated Aju University, and then after that, I was a researcher in Korea Transport Institute. But after that, I decided to go abroad for my PhD study, and I got a PhD from the University of Virginia, kind of close to Washington, D.C. in the States. So at the time, kind of fortunately, my project was about the connected vehicles at the time, because at the time there was no term for automated vehicles and connected vehicles, like by connecting with DSRC and then GPS tech or something like that. So at the time, was more like I was in civil engineering, but my research project was about some kind of collaboration with the mechanical engineering. So that's kind of motivation and leverage to have some knowledge from the GPS tech itself and the communication itself. So gonna talk about that thing through the next lecture. And then after my graduation from University of Virginia and got a first job as a PhD in Florida Atlantic University close to Miami. So at the time was, University of Virginia is kind of one of the known and big universities. So most of the research project was about automated vehicles or connected vehicles or something like that. But Florida Atlantic University was actually good, and then the job position was just a stable, was okay. But the research project was like a more regional level, like enhance the traffic operation on some kind of corridors or something like that. But at the time I decided, I think I have to turn my direction to the kind of go back to the kind of more national level research projects like GPS or automated vehicles or mobility or something like that. So let's move. And then at that time there was some kind of story, but anyway, I got a job from the Technical University of Munich, one of the kind of top universities in Germany, like a KAIST. So at that time was a really, really great experience because, the Technical University of Munich, let's say there's one professor from transport engineering, and then under him, like a boss, there are 40 or 50 researchers were there. So the research area was super colorful, and more than 10 PhDs, and the research group were 3 and 4, and they even have an office in Singapore and some other places. So I could have a lot of opportunities to to do some research, automated vehicles or simulation or traffic safety, or maybe international collaborative project with the European things. So that was a really super great experience. And at some point, I got a job from Korea Transport Institute. So at that time, my job was about the national automated vehicle research project planning and just conducting those kind of research. So this is my career, and now I'm in Ash University. I kind of went back to my home university. So now I'm doing lecture and then research in automated vehicles and some other areas. So if you are more interested what we are doing now, then you can, this graduate school, as far as I know, you guys has already the LinkedIn network, but we also have this kind of network. So if you have something to interest, then come visit and follow our news. Then we can be connected. And then, or we have a webpage, web.aju.ac.kr. But probably the same news will be uploaded. So LinkedIn or this kind of website, you can follow our news. So, and then our master and PhD degree students. And this is the ongoing research project from my lab. So mostly the automated vehicles or AI-based safety prediction system or some other different things is a smart city project. I will talk about that later. So this is how our lab looks like. So we are kind of startup. I've been here 4 years in Aju University, so my lab is now getting growing. So now 7 or 8 researchers are there. So probably you guys are bigger, but we are kind of a growing startup, I would say. So during my introduction, I would like to introduce one specific part from my PhD dissertation, because that's probably a great way to define myself. At that time, my research topic was like that. Automated vehicles, that is great, sounds great, and that looks great. And then automated vehicles, their safety applications and safety capability, that will be great for human because they will replace what we have to do in driving, right? But thinking about that, what about if the sensor, that accuracy is not that good? And what about the GPS positioning error is there, so they don't know where they are? What about the communication has to be transmitted on time but delayed, like 2 seconds? Let's say now you are in danger, but communication delay is 2 seconds, that the warning signs will be transmitted after the accident. So at that time, I actually, as a transport engineers and civil engineers, I didn't like that assumption, because on traffic engineering, transportation engineering, civil engineering, every time we talk about automated vehicles, we say we just assume there's no GPS errors or communication delays. But that's very naive approach, and I would say that's like the kind of talking like I don't know about the GPS or communication delays, and I don't have any methodologies to evaluate that performance, and I actually cannot do anything for that, right? I didn't like those kind of things. So at the time, so I decided to make another evaluation framework, even to evaluate the sensor performance. At that time, the topic was connected vehicles. It's like 2012 and 13. I got my degree in 2013. So at the time, it was just a connected vehicle. So I didn't have any LiDAR or radar, but GPS tech and communication delays, that was important. So at that time, so I decided to make a simulated framework to evaluate the GPS accuracy and communication delays. So I will talk about this in detail through the network. So the main topic is anyway made a kind of simulated framework to evaluate the sensor performance and ultimately to evaluate the automated vehicle safety system in consideration of these sensor performance. Not just assuming GPS error, communication delays, there's no those kind of errors. I didn't like that. I didn't like that assumption. So that was my topic. But at some point, actually my research topic is automated vehicles, and another pillar is a smart city thing. It's pretty different thing. This is more like urban planning. But there is a reason. During my period in Korea Transport Institute, at the time, most of my job was automated vehicles, those kind of things. But at some point, the Korean government decided, let's go for a smart city and let's do some smart city project. But at the time, is there anyone who has a major in smart city engineering in your bachelor degree? Probably not, right? So there's no actually expert, or there's no PhD from smart city or engineering. There's no those kind of people. So at the time, they collected some people, and in Korea, the main solution and main kind of advertisement thing was automated vehicle and automated bus, automated shuttle. So they collected some people from automated vehicles, and I was one of them. So I got an opportunity to design the automated shuttle planning and operation, and even some point, I was appointed as a planner for mobility services in this area. So, that's the reason why I kind of entered this kind of area. At the time, I was kind of challenged because I didn't have any kind of urban planning or knowledge. So at the time, I had to learn about that, which is super different from automated vehicle technology. But anyway, at some point, that was a really great approach, because urban planning things for smart city thing, automated shuttle, that's a pretty different thing. But at some point, the middle range was like, so how do we design our urban area, urban network, or road traffic environment so that the city can be operated with automated shuttles or other mobility application in terms of a smart city concept? So actually, that was a really different topic, and that was kind of one of my challenge. But anyway, that was a kind of, I would say that is a very great point, and I was lucky to have these kind of projects to make an experience. So now, So actually, my kind of research goal and career, I would say, I think I have to confess, I don't think I'm very deep in some kind of specific topic or specific methodology. Maybe AI? Yeah, I'm using AI. And NLP? I'm using NLP. But I don't think I'm very deep in those kind of data scientists. And I don't want to be actually. Just want to using that very well. So sometimes I would think about that. It's kind of PhDs and then professors, they want to kind of pretending and they want to becoming like kind of super expert on specific topic, right? But I thought my passion in my mind, that's somewhat different. I'm kind of interested in many areas and many topics. Sometimes UAM, sometimes automated vehicles, and talking with, let's say, Ruben or some others. Wow, that's a great idea. Let's go for it. That's my instinct. So this kind of decision is like, let's just pursue my passion in my mind, not just pretending I'm a good scholar and I'm a very kind of insightful scholar in some specific topic. Instead of those kind of pretending, I'm just going toward like the merit of breadth over depth. Depth is important, but I respect that. But my goal is something like that. So I'm gonna do everything for designing and making efficiency optimization of mobility operations. So it's like everything about automated vehicles and mobility operation, but that is my approach. So now I'm doing automated vehicles and I'm doing smart city project in actual project and I'm doing UAM vertiport things. I'm kind of happy with that because having new things and new knowledge is my kind of happiness. So that's my kind of career in my research things, my research journey. So let's go back to seminar series. There are actually many areas to be touched from transport engineering. And among them, I kind of pointed 5 points. So first of all, the tech safety performance and even the automated vehicle evaluation scenarios from traffic engineers, the general way of doing is just interpreting traffic accident report and then making scenarios like a human mistake. But automated vehicle is not human and some kind of, I think, the approach is not so methodological or systematic. So I decided to use some NLP things to evaluate making scenarios. And then I think AV should be mobility. Have you ride the automated vehicles, automated shuttle or bus or anything? Now the automated vehicles is like super slow. And then some people there and then stopped. And override, people stop. You know, we are making automated vehicles and not just we are making automated mobility solution and not just automated vehicles, I think. So I decided, okay, let's make it faster, like mobility. But the application wasn't needed, so I used the mobility applications of emergency vehicle. So using that applications, I was kind of try to find the great combination of vehicle parameters to make it faster and make it safer. And then, you know, automated vehicles has a lot of sensors, LiDAR, radar, or GPS, or a lot of things. So what about using that sensors like a mobile infrastructure sensors? So this research is all about that. And simulation, I'm not gonna talking very in depth here because here is Professor Ini Kim, but I'm gonna just introduce very in brief. Yeah. Okay, let's talk about exploring the impact of automated vehicle technology on safety performance. You know, everybody knows automated vehicles, they are not human. They also have eyes and ears. So eyes and ears is a LiDAR or radar or some kind of ultrasonic or GPS communication or something like that. But this is actually the mimic the human. So if their eyes and ears, they're broken, but the safety performance is broken. But in transport engineering, I think our problem is we don't think about that, the ears and eyes, their problem. Because we don't have a knowledge or we don't have a capability. So for those kind of things, we have to do make a kind of naive assumption. There's no errors on GPS or communication or something like that. So, but if you see this, here there is many GPS technology, GNSS and DNSS, DGPS and SB, SBAS and PPP and OmniStar. There are actually many positioning systems, but they have a different accuracy level. But what about in vehicle? Maybe RTK? K is missing, sorry about that. What about the RTK? RTK is a centimeter accuracy, so probably having that in vehicle would be a great idea. But think about that. RTK is like $20,000. Will you like that, those kind of vehicle having $20,000 of RTK? And what about the GNSS, 10-meter accuracy? Now you are really in danger, but your system will be, hey, you are kind of far distant, 10 meters away, so don't do that anything. You're gonna be in danger, right? So what is actually the optimal technology and what is the impact of it on safety performance? That was kind of my research area, research interest, and at some point there is even GPS errors, especially in city level. Have you drive in some very dense area in Seoul City? Then navigation say like you are on different track or you are kind of out of route because you are on route, but this is recognizing your location is somewhat there. So there are so many GPS error things, and they will affect on safety performance, and they will be super bad for your safety performance. And then what about the wireless communication? Well, wave technology in Korea is 27 megabps and a 5G 10 gig bps or 100 gig bps. But anyway, there's a communication delay because even 5G data rate is super fast, but there is a communication delay, even 4G LTE or 5G VTX. Then we have to think about that, the kind of ears and eyes performance like GPS accuracy and communication errors. So from transport engineering, we say our automated driving approach assumes that there's no positioning errors or communication delays, but relying on that assumptions can be kind of more, it's actually, I would say it's naive. So, before some years, at the time we transport engineers, we just do our things, and mechanical engineering, they do about the GPS device or communication itself. But now, actually this is my kind of path to my research. I would say even though we are civil engineering or transport engineering, we have to think about the device performance as well because automated vehicles and automated driving, that is based on that device performance. So this area, this is obvious, and this is some kind of integrated things, and that area, that's my kind of path for my research things. So this was like a simple result. Even I tested the communication delays with the distance between transceivers, like a distance between, let's say, vehicles, and then total number of vehicles. Think about that. Probably there is some kind of transceivers, like you probably use a KT, SKT, or LG Plus, there is some kind of a transmitter. And then, there are so many people inside the transmit cell, then there could be some kind of delay. And what about the distance? Like 1 kilometer from transceiver, communication performance is going low. So based on those kind of things, I used some communication emulator to assess the communication delays. And based on those results, I made these kind of logic model. And then GPS tag, Actually, RTK is a super accurate and autonomous GPS. That's just a GPS in your smartphone. There's a 10-meter accuracy, the positioning error. So this means, true unsafe, that is actually a good thing. And false unsafe is like you are actually in danger, but the safety system say, hey, there's no danger. That's a super bad thing. So, if you use just a commercial GPS in your automated driving system, then you're gonna have a lot of false warning like you're safe, but it's wrong. You're unsafe, it's also wrong. So, this result is saying that if you use a bad GPS tag, then it's gonna be the safety performance is not reached. It's not satisfied. So at the time, I had to make a simulated framework even to evaluate those kind of GPS errors and communication delays. So that was like a kind of very challenged work because, anyway, I used the microscopic traffic simulation model, VSIM, but probably some of you guys know about VSIM, but VSIM just reflects a 2D simulation. It has an attribute like a height and elevation, but vehicle doesn't respond to the elevation. So, and then there's no any kind of 3D attribute. So, but GPS multipath errors like a building and conflict, I had to have an element about the kind of elevation of each object. So at the time, I collaborated with the mechanical engineering department. We made a height map, and then based on height map, we made a kind of satellite visibility map. It's like a kind of super micro data points, just like a LiDAR data. So we made this kind of satellite visibility map. So let's say here there are so many buildings surrounded. So multipass error is like a percentage of that is at some specific level. And here is open space, so there's no GPS error or something like that. So based on the vehicles are moving around the simulation network, they are evaluating their location based on satellite visibility map. And then the communication emulator is not actually fully integrated because this and VSIM, there was no way to integrate these things. So that's the reason why we tested the communication delay and its probability from emulator. So based on the result, instead of doing like an integrated approach, we decided to use this kind of model. So communication delays was actually calculated. So based on those kind of integrated approach, I was just conclude this thing with this figure. And this figure is a base thing is just a human driving. So conflict is like many. And transport engineers, we do automated vehicle research is like, hey, there's ADAS system and there's some V2X ADAS, some safety performance. So if you use automated vehicles, then conflict will decrease. It's like that, like a 30% good. So it's super good, right? That's how we kind of insist through our research. And, but here, 30% decrease. But if you use RTK things, it's just super centimeter accuracy level, then the result will be just similar with this, because this is assuming ground truth and there's no error. But what about just the commercial general GPS in automated vehicles? Thus, the conflict things is more even than human driving. So that means if your vehicle just using very low level GPS tech and communication delays, then it's gonna be worse than human driving, even though your vehicle is automated vehicles. So at the time, FHWA or Federal Highway Administration, they were wondering about, so this is bad but cheap. Thus is really good but super expensive. So what would be a great level for commercial vehicles? What about OmniStar GPS? What about DGPS or something like that? And this thing, no. for safety things because lives matters, right? And then RTK is a super good. Maybe future we can apply that, but there's not commercial level for now because too expensive. So they wanted to explore these kind of impact of accuracy on safety performance, and that was a kind of one good shot of the result. So this thing, I would say this is naive, even though I have to make these kind of assumption in my research because sometimes my focus is not sensor performance and I have to make this assumption. But the thing is, I made a kind of another approach, not to assume these kind of things. So that was my PhD dissertation, and even now I'm kind of kept my ways on these kind of research with the sensor performance. Okay, that was the first thing, to do some automated vehicle research from transport engineers. And second thing is, some of you have probably the project about automated vehicles to create evaluation scenarios because automated vehicles has to be tested, right? But the scenario making is like from transport engineering, like we just investigate in which condition or in which situation the human make mistake many or maybe in danger. So that's kind of a simple way. But I would say, well, traffic accident data, there are so many elements and so many, 30 or 40 elements about like a numbering. Like, how can I say, the sunny days is a 0, or rainy is a 1, and then date time is a number. So everything is actually a number. Place, 대전, let's say 399 or something like that. Everything is 9. Everything is number. But there's only one column to describe how the accident happens. It's like a police officer say, number 1 vehicle was approaching to the entrance of apartment, and second, the pedestrian was approaching or something, and then first vehicle didn't see any kind of signal, and they were conflicted anyway or something like that. It's more like a descriptive, but this is more like just a fact. Well, if accident happens in rainy day, can you assume, can you kind of make it certain like the accident cause is because rainy? Can you say that? Maybe, in rainy day, I just made another mistake. It's rain, just the rain comes and that doesn't matter. So, we can make a misunderstanding from these kind of things because there's a rainy and then so the pavement is not right. So accidents happen. That's our understanding. But in fact, actually there's no, because if you read these kind of description, it's just a human mistake. It's like I didn't see the green signal or red signal or something like that. But there's a one column, but not many people have used that narrative descriptions before to create evaluation scenarios. What is the reason? What will be the reason? Can you guess? Because some years ago, we didn't have a methodology. So let's say there's a 10,000 traffic accident record. And I, as a professor, I will order you guys, okay, each people analyze these things like, okay, 1 day, 100 record, 100. Okay, well, do something. That's really kind of, labor things, right? But now we have an NLP. So one of my kind of research pillar is making this be analyzed. And what about the fusion of structured data and unstructured data? So extract some important information from narrative and some other information from structured data, and let's interpret the traffic accident situation based on these kind of comprehensive information. That was a core idea. So actually, first attempt was made 2016 and 17. At the time, I went back to the Korea and I thought like I was kind of aggressive in my research, so I'm not gonna do kind of normal approach, and I'm gonna do some kind of fantastic approach because I went back in Korea. I was kind of had a lot of passion. So at the time, I used the TF-IDF methodology, and if you studying about the NLP things, this is like a kind of former model before the transformer or well, XGBoost things. So at that time, I analyzed these things based on this using this methodology, and just to find out what kind of wordings will be kind of frequently observed, rainy or maybe a left turning. So just connecting by like frequent wordings and made an evaluation scenario, and that was the first approach to apply the NLP. But now I'm going more deep because we have a great NLP model now. It's like a transformer. The tension mechanism was fantastic. I'm not gonna talk about that this is not really a theoretical lecture, so I'm not gonna talking about the tension mechanism and transformer and BERT. But anyway, transformer and BERT is a pre-trained model for language. It's a really great advantages. So now I use we actually use the BERT model to interpret the structured data, unstructured data. And now we had some kind of simple test, and then now structured data only, actually among these kind of model, BERT was best, but the structured data was like a F1 score was a 60 or something, and the unstructured data only is a 70. And if we use these things in fusion level, then the accuracy is increased. That means BERT was more interpretable if she use integrated data with the structured and unstructured data. So please do something with that thing because it's gonna be kind of, actually it's the same for human. If you see that the structured data and see the unstructured data, read about that, you will have a more understanding on how this accident happened. That's actually the same for humans does. So now we didn't create the evaluation scenario based on this approach, and that is still ongoing. But our next step is actually, developing evaluation scenarios based on by integrating structured data and unstructured data. So that's our next step. Okay, and what will be the next? What will be some other parts to do with the automated vehicles from transport engineering? I will be very in brief for these things. So there was an interesting news. Cops pull over Google car because that was too slow. Because you're probably understanding because automated shuttle, automated vehicles now, it's just super slow, and then keep braking because to prevent any kind of dangers. That's understandable, but that is not mobility, and I won't use that for my commuting and for my business trip, for my family trip. No, probably not, because that's not mobility solution, and that's just a technology, and that's not mobility solutions. So I wanted to find the great combinations to keep safety, but also kind of make it faster. So, but I needed the use case. If I say, hey, I will make just a passenger automated vehicles faster than others and safer than others, and then people will say, hey, why that or he or she, that automated shuttle has to be faster than others? It's not normal, right? So I brought the applications of emergency vehicles, like ambulance or police cars or something like that. So police cars and an ambulance has to be fast, right? Has to be fast, but anyway, keep safety, that matters. So I just brought that things and emulated and simulated in FSM using EIDM. Probably some of you guys probably doing this kind of research. And EIDM model, there are a lot of parameters and desired time gap, maximum acceleration, desired deceleration, or many things. And I also had to define the lane change behavior, something sometimes aggressive, sometimes non-aggressive. So I defined the lane change behavior with this, because if you thinking about the people's logic, when they do lane change, they thinking about like a benefit first. Let's say I want to do change my lane. Is that be kind of advantages for myself? That's the first decision. And if you say, okay, I have to do lane change because that's beneficial, then second you think is a possibility. So is that possible? So there's a lot for lane change. So I made this kind of logic for defining driving aggressiveness over AV. So there are many parameters. So scenarios like a combination of parameters, 200 set, 116 set, so total 3,040, 56 scenarios. So there are so many simulation redundancy. So based on, so our measure was conflict, traffic, number of traffic conflicts. Another thing is travel time saving. So if the parameter, the combination of parameters and the result is somewhere here, it's just for safety. It's like an automated shuttle now. And here, it's a fast, but safety is bad. It's not very great solution. So I wanted to find out, searching for the combination of parameter and their range to balance in safety and mobility, those kind of parameters set. So anyway, well, based on this research, we found some kind of a range of the driving parameter sets to satisfy not only the safety but also mobility things. So that was one of the kind of touch-up things, aspect from transport engineers toward automated vehicles. So how to categorize that things like mobility focused or balanced things? Well, just use the k-means clustering. Probably you know what that is. So I'm not going to talk about the k-means. But anyway, to classify the area for this area is for safety focused, and that area is a kind of balanced. So that was our approach. So I made a paper for IEEE. Yep, the last things, just the 3 minutes. So sometimes, think about the LiDAR, radar, and then camera image, and then GPS tech, GPS or positioning things. There's so many data being produced from automated vehicles, right? It's like, automated vehicles is like they have a great eyes and ears, so they are hearing and see. So many data are collected. So why don't we use that collected data from automated vehicles as a kind of sensors? So let's say, so we actually co-worked with Dr. Hyung Kim from, I'm not sure about that, the English name, 차세대 융합기술원 in Gyeonggi province. Hyung Kim got a PhD from here, right? Yeah, got a PhD from Professor Ki-tae-chang. He was one first or second PhDs from Professor Ki-tae-chang. But we have a very close relationship. So this Zero Shuttle is collecting so many data, like as I said, LiDAR sense data, radar sensor data, or something like that. And actually, we decided let's find out some kind of, how can I say, not very familiar situation in road traffic environment to automated vehicles based on the sensor data. So based on the Zero Shuttle, the data, we actually categorized like a driving behavior pattern and data patterns. So, let's say there is 6 different categories in terms of driving behavior or data signature, and then we actually investigated each area. So what happened there? So Zero Shuttle data things is somewhat different. Then we investigate what happened there. And some of the area was just a different behavior because they are left turning through or right turning or sometimes stopping. That's a normal behavior and in the range of normal behavior. but some of the areas was kind of abnormal, and we investigated that area, and we find out that the road traffic environment was not that was not that kind of great for automated vehicles at least. So that is a kind of way of searching for some kind of dangerous situation or not advantaged situation for automated vehicles. So that was kind of our idea. So this is just the entire framework. So hybrid sum k-means and then k-means plus plus. It's all about the classification model. So I'm not gonna talking about each model itself. But anyway, the k-means, the data signature and driving behavior patterns, we collected those data and classify them data like based on hybrid sum, k-means, clustering approach. And we got actually 6 categories. We investigated each category and 1, 2, 3, 4, let's say 1, 3, 4, 5 maybe. That was just a safe situation. That was actually nothing. It's just a normal behavior, but it's different. But cluster 2 or 6, there was some kind of weird. It's like here abnormal situation is like cluster 5, and this is cluster 2. That was abnormal situation. So we investigated that road segment, to find out what happened. So if I just made an example, so this cluster 5 was like this. So automated shuttle is driving at the kind of rightmost lane, and the automated shuttle has to turn left and has to having like multiple lane changes. And at that time, the data signature is saying like too many acceleration and even stopping on the road, because on the stopping on the road, it's actually prohibited, but automated shuttle did. And then some emergency light was on, so somewhat weird situation. So we say, okay, this area is not that great for automated shuttle because that has to be done like many lane changes. So let's say, let's make some kind of lines is like some kind of right turning things or something like that. So we are still finding out some kind of insight and some kind of improvements from these kind of results, but that is only one thing. And I would say the good thing of this approach is we used automated vehicles data as a kind of infrastructure sensor or as a kind of sensor to investigate which road segment was great or bad for automated shuttle. So that's another approach. And maybe you guys can do a lot of things based on the sensor data, because sensor data is huge. So we are still searching for what kind of research we can do as a transport engineer using that sensor data. So we're still doing things. So we are waiting for the second step of this. But anyway, that was a kind of first approach some years ago. Okay, actually, I'm not gonna talking about that things because it's a simulation. And actually, this is one of the part of my PhD dissertation 10 years ago. At the time, the traffic simulation was great for making traffic scenarios, but vehicle trajectory was not that realistic. Thus, vehicle trajectory is realistic, but it's not great for traffic scenario creation. So I decided to integrate these approach. So I produced the vehicle trajectory out of the traffic scenarios and post-processed by the vehicle dynamic simulation. That was one idea. So maybe if I got another chance to share these kind of seminar things, then I'm gonna talk about that in detail. So now in our lab is like these kind of is making like this kind of traffic simulation interface as well, because just one message is we are engineers and we are can I say the researchers, but sometimes we can make it better, make our algorithm better. It's like solutions. So our lab is I wanna make it, all the algorithms like a solutions and some kind of commercial use. So we always use making these kind of interface. So please do so, maybe in collaboration with some other companies. So making it just like a solution, not just the algorithm. Because in business level, if you see, or if they see your algorithm, then they will say, hey, this is just a combination of some numbers and it's not at practical level. But if you do some effort on that, you can make it like a solution. Then business level, they will say, wow, your solution is like a kind of ready. So we're gonna put some kind of effort, then it's gonna be great or something like that. So you can approach for that business things. So that's the reason why we made this kind of simulation framework. This is a simulated evaluation framework for automated vehicles, and this is a kind of real-time performance check interface for automated vehicle. So I'm not gonna say in detail. So just want to conclude my presentation with this one thing. So I'm thinking, I'm kind of, there's one research area in transport engineering is like a human behavior, right? Maybe many professors, they're doing human behavior. But what I'm interested in is not human behavior. I'm interested in automated vehicles behavior. So I'm kind of thinking like I'm kind of checking this wellness of automated vehicles. And this is the wellness checkup for human, and that's the process of it. So if I just using this, then I can say we have to have a capability to examine the ears and eyes of automated vehicles, which is sensors. So not just not just making an assumption like there's no error. Then instead of it, let's make some kind of approach and method even to evaluate the eyes and ears performance. That's the one of the approach. And second is please ask automated vehicle, something bothers you? So what kind of road traffic situation bothers you? Then you listen to their voice. Maybe there's no voice, but you have to make a kind of approach, how to identify those kind of situation and who is bothering automated shuttle, right? And then you have to make a kind of evaluation scenario as well, because if you want to check the performance of automated vehicles algorithm, then you have to make a kind of checkup process, like with the evaluation scenarios. Immunization is, important. So in what situation AVs can kind of resistant to challenging situation and operate sustainability? Then to identify that, you need methodology, and then lifestyle, we have to make it mobility solution, not just a vehicle. Because, vehicle itself, and if you just make a kind of very big vehicle tech, it's gonna be valued. But, in real world, there are so many use cases. Maybe I just want to move my alone, I need just like this size of automated vehicles, because I'm gonna just moving around in the building. Then it should be smaller, right? So based on the use cases, the automated vehicle has to be changed, and then maybe sometimes should be fast and should be sometimes safe. So you have to thinking about you are making mobility solution, not just the vehicle itself or vehicle parts. Yeah, maybe you are mechanical engineering, then it's gonna be different story. But as a civil engineering and transport engineers, I think you have to thinking that way in your mind. So I have a limited time, so I was kind of fast. So I'm gonna conclude my presentation in here. So if you have any kind of question and comments even after this presentation, so please contact me, and I'm ready to collaborate with you guys and in any topic. So I'm already very close to kind of working with this graduate school, so I'm around. So let's keep that discussion. Thanks. So thank you very much, and that's I said, right? Yep. So thank you.